In Calculus 2, when you guys were learning all the different techniques of integration, your main goal was to make your integral look like one of 9 or 11 really simple integrals. And the first technique that you learn in dealing with that is to do a U-Substitution. So beyond that, you did some integration by parts, and then you did some more other types of substitution, like a Trig Substitution. And then there were other substitution methods in algebra or in calculus that you may or may not have gone over. Like, there's some substitutions where if you have some cosine and sine combinations, you do some tricky substitutions. But the idea is to make your integral look like one of those 9 or 11 basic integrals. So some sort of power rule, ln of x, a cosine of x, all those things. And so we're going to go through the same ideas, same basic concepts of substitution to make your differential equation look like another type of differential equation by doing some sort of substitution. So by substituting something, you might be able to make your differential equation look like something that we've already solved or something that we know how to solve, so that we can go ahead and solve. Just remember, when you do substitutions, the idea of differentials will be important for us, because we are dealing with differentials, just like our basic U-Substitution. So this section is dedicated to substitution of certain things. Along the way, we'll take a look at different types of differential equations and how they might look like. This would kind of go on top of the classification of differential equations already. We know how to classify differential equations by order, by linearity, if they're linear or not linear, and a few other things. And after that, we want to be able to identify if a differential equation looks like of a certain form. Like if it's separable, we should be able to look at something and determine whether it's separable or not. We have the differential form where we have m times dx plus n times dy. And that's another form that we've seen, and so we can check if something is exact. So now we're going to define other forms and other types of functions so that we can further classify a differential equation and then be able to have more tools to solve for the differential equation. So our first definition here is a homogeneous function. Now, I'm sorry to say that the word homogeneous has been used in a bunch of other topics, like linear algebra, for example, and also in differential equation, to mean something a little bit different. Homogeneous in my head, the way I remember it, is that it's something set equal to 0. Unfortunately, this is not what homogeneous means. The homogeneous function of degree n is a function where if we replace the variables x and y with t times x and t times y, we can somehow collect and factor out those t's. To just be of one power. So that's the definition of a homogeneous differential equation. And your first order differential equation is homogeneous if both of the functions m and n are homogeneous functions with the same degree. And if that's the case, we can do a substitution to maybe make the equation look exact or make the equation look like it's separable. But this is the trick to it, is a substitution. Now, one of these substitutions might lead to a good answer. The other one might lead to a bigger headache than you started with. So just like when you do integration by parts, when you do an integration by parts and you set u equal to something and dv equal to something, and you go to the next integral and say, oh, that looks more difficult than it was before, then you have to stop, backtrack, and try again. So that's the same thing over here. You got two possible scenarios. One of them, they both may work in your situation, or one of them would work better than the other in your situation. You have to kind of know that, and you'll just figure that out by practicing a lot. All right, let's do an example. Let's do 5. Looks harmless.
Will the problem always tell us if it's homogeneous, or will we be expected to identify?
I think it's. I think you have to be able to identify it. Should we do it here? Maybe we'll do it on a new page. So if we look at that, we could check if it's exact. It probably is not. Take the derivative of this thing with respect to y. The first one with respect to y, it's 2y plus 1. The derivative of this with respect to x is 2x, and they're not equal. So it's not exact. So let's check if it's homogeneous. So m, for starters, is equal to y squared plus y times x. And what they want us to do is they want us to put t times x and t times y in for x and y. So I'm going to get ty squared plus ty times tx. And then if I take a look at this and I factor out a t squared, then I have a t squared times the original m function, and so I can say this is homogeneous to degree 2. Now, for this whole differential equation to be homogeneous, I need to check the other function and show that it actually has the same degree, degree 2. And if it doesn't, then maybe it's not homogeneous and we got to do something else. So it's x squared. So I'm going to look for all the x's and replace it with t times x. I'm going to look for the y's and replace it with t times y. There are no y's. So I'm just going to replace the x with t times x. And I can factor out a t squared. And then it's just going to be t squared times the original n function. So now I have the second function, n, to be homogeneous with the same degree, degree 2. Okay? So now the next step is to make a substitution, and we could choose to let y equals u times x or x equals v times y and see what happens. So let's try the first one, y equals u times x. So what we're going to be concerned about is the differential for y, which is dy. So what we're doing is we're taking the derivative of u times x, and we have to assume that u is a function of x and x is a function of x. So what's dy equal to here? Derivative of first times the second plus the first times the derivative of the second. So this is the product rule. So let's do the first times the derivative of the second plus the derivative of the first times the second. So by doing this, what we're doing is we're essentially replacing your dy with something else, aside from replacing the y's with something else. So this is our substitution. And now what do we have? We have y squared plus y times x dx. Is that right so far? Minus x squared times dy. Y dy. Now, dy is this whole thing over here, right? So now if you take a quick scan over this whole thing, we see that there's no more y's. Now I'm looking at this as a u, as a function of y. So we might be interested in solving for u now as our differential equation. Let's see how this is going to turn out. We have u squared x squared plus u x squared dx. Let's distribute this. X squared u dx minus x cubed du equals 0. That okay so far? Notice anything? It looks like the negative x squared u dx and then u x squared dx are the same, right? Except with opposite signs. So it looks like we might be able to cancel that out. And then what do we have left? We have u squared x squared dx minus x cubed du equal to 0. And this might look what? This might look separable, right? Let's see if we can separate this. U squared x squared dx equals x cubed du. And let's bring all the x squareds over to the other side. I don't think so. Well, you can divide out and then the x squared over x cubed. I'm going to write my u side to be u to the negative 2, so it doesn't force you, or it doesn't tempt you to use the ln, because the integral of 1 over u squared du is not an ln function. Okay, so far? I think we're looking pretty good here. We can actually solve for this differential equation. Now, we probably want to solve for u. Or, I guess, yeah, when we solve for u, we put it back here and get y by itself. So let's integrate this. We will get an ln of x on one side and a negative 1 over u on the other side. Let's see. Let's put the plus c on the other side. So if we solve for this, we get u equals, let's see, the reciprocal and the negative sign. And I don't know if you can simplify that anymore.
You get rid of the plus c altogether?
No, I didn't. I need the plus c over here. Oh, wait. Oh, we got to be careful now. Yeah, it has to be in the denominator.
Or you just switch it. Well,
Is that?
yeah. Is it okay that I know it's whatever, but I was looking at it, plus c when it's on the right, so I subtracted it from the left, and then multiplied through that negative, and then made it c minus ln.
I think changing a c from plus to minus isn't a big deal. Yeah, multiplying the c by a number wouldn't be a big deal either, but doing the subtraction like this, it is important to keep it as a denominator.
So then I could technically write u equal 1 over c minus ln x. Just looks nice to me, but
Yeah,
it's not good.
yeah. So you can take this negative sign and distribute it in the bottom. Okay. But just like the U-substitution, after you do your integral, we went into the U world to do your integral, and then we have to put it back to the real world with x. And so here we introduced some function u, so we went into some other world. Now we need to go back to the real world where it's just y's and x's. Yeah, we set y equal to u times x. So if we do that replacement back, we found u, and then we just multiply this by x. And now we have the general solution. Well, in this case, this technique is looking at homogeneous functions. And if it's not homogeneous, then this substitution probably won't work. Alan?
Yeah, it's basically the same thing I found finding that keeping
Well, the idea is that when you do the substitution, it's set up so that it looks like it'll be separable. It looks like it will end up being separable after you do the substitution.
I was wondering if it is also a reverse process. It seems the same principle will apply in which one is famous. I wonder if this is the reverse.
Oh, yeah. I mean, that's probably how people came up with this idea, is that they're trying to solve for these differential equations that doesn't seem to have a process or a solution. So let's try some substitutions, and then looks like we can make it separable somehow. Now let's look back at the original function and say, hey, look, there's something special about these functions. It turns out that they have the same powers. If you look at this is y squared, this is x and y put together. looks like they are together, and this is x squared. So if you have that phenomenon, then that's how they probably defined.
And I also wonder if there's like if we do the other way around, for example, if we switch x equals to dy, will all this become like x here?
I don't know. In this case, it might not. It might be just as simple. But there are cases where one is going to be clearly easier than the other. So I don't want to try it right now. But you could try it and see. Do the other substitution. Let x equal v times u, and then see what v times y, and see what happens. Right.
Back in the let y equal to ux and the next line particle, was that in respect to y?
Well, it's a differential, and then we can think about these as functions of each other. So it's like it's saying it's a differential, and these are functions. And so by saying it's differential, we're not assuming that one of them is a function of the other. We're just treating all of them as if they're all functions of something.
Should this be linear or should it be linear?
Have you guys done anything like this? Anybody?
I mean, it's really made it look really easy. And it's like, yeah, I could probably do that again, but if you give me something different, I might do that.
Well, the only different scenario you would come up with is that it'll say x equals v times y, which you'll do the same thing. But it's like the U-substitution that you had, and I'll do this really small. The U-sub in Calc 2, when you let u equal to, I don't know, sine x, and then du equals cosine x dx. So it's kind of like the same thing. Well, it's a little bit more complicated because there are two things that you're multiplying, and you end up having to, you're forcing a product rule happens. Maybe this isn't a good example. But the idea is it's a differential. It's like saying you're taking the derivative here with respect to x, but then you're tacking on a dx at the end. Maybe it is a good example. I don't know.
Well, I mean, in that U-sub case, it's what you usually
So-
it's a function of y or something on the other side, and you do this U-sub, you go to dx on the right, because there's a dy
Right.
applied on the left or something.
So you can think about it as chain rule. It's dx because you're taking the derivative of this variable x.
Yeah.
So now if you treat this as two separate variables, then it's the derivative, so it's the first term times the derivative of the second, so the derivative of x in differential terms is just going to be dx. And then the second times the derivative of the first, and the derivative of the first is just the du. So I guess when we're doing some sort of substitution, these idea of differentials would be important for us.
Does this happen in other places?
There's going to be other substitutions that we're going to do.
Yeah.
So I don't know if it'll be a product rule like this or just a simpler substitution. We'll take a look. Yeah.
What do you know? How do you know when to let the x equal to
Yeah, so I don't know, just by practice. Not quite, because you're not doing partial derivatives. I guess the key is that these are differentials. So a differential is that instead of taking the chain rule, taking the derivative of the inside, the derivative of the inside is just d something, whatever the variable is.
So what you said about practice is just like trying to make it easier for yourself, whichever one makes it easier.
Yeah, so like we did this one, and there was a happy cancellation over here. But if you do it the other way, I think the other way would give us the same similar scenario where it would be just as easy. But I've seen some problems where you do one way and then you start, it looks like it's a lot more complicated, but then you do a different substitution, it turns out to be way easier. So I can't come up with those examples off the top of my head, but you'll run into them, I'm sure. Alan?
Try doing it the other way, because I started doing it in Student 2, and I think we
Came up with the same.
came up with that it doesn't get better, it might get worse, and so make sure we're doing it right.
Oh, well, so do we want to see it the other way? I guess that's what we're moving towards, right? All right, let's.
Can you do this multiple times, sort of like integration by parts?
No, I mean you can, but I think after one time and it's still not happening for you, then it's a good time to quit.
First you don't succeed, give up.
Let's say if at first try your integral looks a little bit more complicated, then maybe you should try the other way. Give up that first way and then try the other way. Not totally give up. All right, so we'll try x equals v times y, and then we'll see what happens. So just like before, we need to do a differential, which is a derivative of a product on the other side. We have y dv plus v dy. And then make your substitutions so the y's will stay, and then my x's will get replaced with vy. So I got a y squared plus y vy dx minus vy quantity squared times the dy turns out to be this big thing. Oh, sorry. Okay. The dx gets replaced. Y dv plus v dy. And then this is x squared, which is vy squared times dy. So all the x's are gone now. And all I have are the variables y and v. Is this right? Oh, parentheses there. All right, let's FOIL this out. We got y cubed dv. That's the first term. The outside term. Vy squared dy. And then the inside term, y, so that's y cubed v dv. And then the last term, v squared
It's the whole thing.
FOIL.
Y parentheses squared.
Oh, wait,
For the second.
first, outside, y squared v dy. What?
The second term on the first factor is y vy. You're multiplying it by v dy, so there's two y's and two v's. It shouldn't just be v times y squared. It should be the whole thing vy squared.
Right. What's the third term he's doing? Y cubed v? Which one? Which term are we talking about?
For God's sake.
That's vy squared times v.
Yeah, that's last one.
I was
I'll get the second term in this thing.
We just out of order.
So you go.
I was foiling it, right? The first, outside, inside, last.
Oh, yeah.
So,
I
I
foiled something, I guess.
foiled again. All right, so I'm in the inside term now. Y. And then the last term. This is your term, Alan. So the y squared, v squared, dy. All right, let's find some. Let's combine all the differentials together here. We got let's collect all the dy's first. I don't know why. Oh, the last two terms match?
Yes.
Oh, good. So maybe it's the same. So I have one vy squared dy term, and then the other term with the dv's looks like the y cubes can factor. I'm going to go ahead and do that. So I have y cubed plus y cubed times v. So it looks like this might be separable. Uh-oh. Whew. My computer would have shut down. It would have taken another 15 minutes to reboot again. All right. So is this, am I doing it right? Does this look okay? Yeah, so it looks like it's still separable. It looks like it would be just as easy. So let's bring the dy's to the other side. So I have 1 plus v over v dv on one side, and then you got y squared over to the other side divided by y. And this is doable. Yeah, you can break this up. So this is integrable, easy enough to integrate without having to do any special by parts or partial fractions or anything weird like that. So this is manageable, and it looks like it would be just as easy to follow through with this. So this would be the case where either substitution would work fine. I mean, the other one was a little bit easier because we only had one term to integrate on either side. This one will have two terms to integrate, which isn't too bad. It might be trickier to solve for v because we need to replace the v again, but the process looks like it's okay. Can I put dot, dot, dot? What? Okay.
Natural log of b plus negative natural log.
So I guess solving for this would be tricky. Solving for v time v plus ln v. Let's see. No. Oh, there you go. So then everything will be in terms of x and y. Say it again.
I was like, wait a minute.
Yeah, so in this case, it looks like we can't make it explicit, but we can present this as an implicit function. And this is graphable. I can graph this in a graphing calculator program. So that was a good move. Replace your v's with x over y's. And then if you do have an initial condition, you can just plug it in here and solve for c. And then if somebody's forcing you to find an explicit function, then you can use
You
something.
could do this. You make it explicit. Natural log of x over y is natural log of x minus natural log of y.
Oh, then
You
cancel it.
multiply into that on both sides, and then you just end up with natural log of x plus x over y equals c. Bring the natural log of x over the other side. Multiply both sides by y, divide both sides by natural log of x plus c.
Is that right? So, and then take the reciprocal. And then multiply by x on both sides. Hey, this is our answer? Or something like that?
That was the way that one is, right?
C minus ln x, yeah. So we got a different c, but, well, there you go. Yay, math. Yeah, so it looks like we got the same result if we follow through. So we've seen a couple of different processes here. In the previous one, we did one substitution, and we took our original substitution and replaced the u with something else. In this example, we actually solved for v is equal to something so that you can replace everything in terms of u and v, or in terms of x and y again. So this would be a good example to look at in terms of comparing, contrasting, and all the different kinds of moves you can possibly do with this. All right, good. You mean the only example. All right, let's move on to the next substitution. The next type of differential equation we're going to look at is a thing called Bernoulli, or something that might look like a Bernoulli. It's a Bernoulli differential equation is a differential equation that looks almost linear, but it's not. It's not linear because, remember, linear means all the dependent variables, including its derivatives, are just to the first power. And the other side here has y, which is the function that we're looking for, raised to the nth power. So it is not linear. But it looks close to linear, right? Except for the y to the n over there on the other side. I think this is different because this is written a little bit differently. We can't separate it like a differential form, and so it looks different. Yeah, so these substitutions take us to different types of differential equations that are unrelated, but there are substitution techniques to help us solve for these things. So here we have a differential equation of this form is called Bernoulli, and if n is equal to 0, then this is just a linear equation, and we know how to solve for linear equations by looking for integrating factors. if it's not equal to 0 or 1, we're going to use a substitution of u equals y to the 1 minus n. And then what's going to happen there is that you're going to force your Bernoulli differential equation to look like a linear differential equation, but that's a linear differential equation in U. Okay, let's try a problem. Let's go for the easy one again. We should try one with an initial value. So that would be like 21 or 22. Let's try 21. First, we can identify this to be a Bernoulli equation. And it's good to kind of identify things. Well, I guess I suppose I would want to get rid of the coefficient of the dx dy or dy dx. So I'll do that by dividing an x squared on all sides. Because I want to make it look just like this Bernoulli equation that they have here. So dy dx equals, or no, not equals, minus 2. I divided by an x squared, so the 2x divided by x squared is going to give me a 2 over x times y is equal to 3 over x squared times y to the 4th. And I wanted to keep the y to the 4th separate so that I can identify what my n is for the Bernoulli equation. I can also identify my p of x and my f of x. So then I can see that for this, my n is equal to 4. It's not equal to 0 or 1, because if it was, then it would be linear. And so my U-substitution is going to be y to the, let's see, what's 1 minus 4? Negative 3, right? So remember, whenever you do a substitution of sorts, you have to find differentials. So du is going to equal to, this is negative 3, y to the negative 4. Am I subtracting correctly? Minus 3 minus 1? Yes. So y to the negative 3, the derivative of y to the negative 3 is negative 3y to the negative 4. And then don't forget to tack on the dy differential. So actually, we can think about this as a du dx and dy dx as well. So we can replace our dy dx with dy dx equals something with a du dx. You know what I mean? So this is going to be a negative y to the 4th over 3. Is that right? But wait, I can't. Just like the U-substitution, when you do a U-substitution, you want your integral to be all u's, right? So I still have this y here, so I need to replace that y with something. What am I going to replace this y by? It's what? U cubed? This thing is equal to U cubed?
Yeah, you keep the
y is equal to u to the negative third, negative 3. Man.
So u is equal to y to the negative 3, and I want to make this to the fourth power, so I would raise this to the negative 4/3. Is that right? So then I would have y to the fourth is equal to u to the negative 4/3 power. All right, let's see what happens. Y to the fourth is equal to u to the negative 4/3 power over 3. This doesn't look easier. So let's replace this with negative u to the 4/3 over 3 du dx minus 2 over x. And I have a y here. What's y equal to again? U to the negative 3 power. 1/3 power. Negative. Equals 3 over x squared, and what's y to the fourth equal to?
First term, negative u to the 4/3, negative u to the negative 4/3. No, not let me look down from the first one. Negative 4/3.
Negative 4/3.
Is it better to put it down?
What?
Is it better to put it down? Put it at the bottom?
I think if you're just consistent with everything, it's okay. So put everything in the denominator if you want. But if we keep it like this, I'll just say I'm going to end up multiplying everything by u to the positive 4/3, or I'm going to divide by this. I don't know, whatever. Something will happen. So here's what I'm going to do, and this is where the magic all happens. I'm going to divide the whole thing by u to the negative 4/3, so that I would cancel with a couple of things, and then this thing is going to be u to the negative 1/3 divided by u to the negative 4/3. So what am I going to have left here? I'm going to have a negative 1/3 du dx minus 2 over x. What's this going to be? U. I hope. Did it? So this guy's just thinking u to the negative 1/3 minus 4/3 minus negative 4/3. So remember, when you're dividing something, you subtract the powers, right? That's what you're thinking, right? So 1/3 minus negative 4/3 is positive 3/3, which is u to the first power. And that's where the magic happens. Now it's linear in u, the u variable. And I suppose we can just get rid of this 1/3, just one more step. We could have divided by 1/3, but I wanted to look at the variable itself and see what happens to the variables. So this becomes 6. So now you have a first order linear differential equation with u as the variable. And do you remember how to solve for that? There's some integrating factor thing, right? This is a mu, not a u. You remember what it was? It was like e to the integral of the p function, 6 over x dx. Remember that?
Yeah.
6 ln x. So let's put the 6 as a power, and then this is just x, 6x, x to the 6th, I mean. So that's your integrating factor. And if you guys have done integrating factors enough times, you know that the left-hand side will just be mu times u, right? So this is d dx of mu of x times u. So we need to integrate the right-hand side. So the integral of both sides would give us mu of x times u. And then the integral of this is -9. And then this is x to the -2. You add 1, x to the -1 with a negative sign plus c. Right? So you want to divide out by mu? Yeah? Oh, you got to multiply this by x to the 6th also. Yeah, I was jumping ahead. Thank you. So let's fix that. Negative 9x to the 4th, right? So negative 9x to the 5th over 5. And then we're solving for u, so we're going to divide by the integrating factor, which is x to the 6th. So this will be minus 9/5 x to the 5th plus c divided by x to the 6th. Negative 9/5 times 1 over x plus c over x to the 6th. So this is what u is equal to, but we want it in terms of y, right? So let's remind ourselves that u was equal to y to the -3, so that we have y to the -3 is equal to this whole thing. I'll just put negative 9 over 5x. I don't know if that's any easier to write. So this is 1 over y to the third, right? Or can I just take the negative third root or something? So I have to take the reciprocal in the third root. So that y is equal to, let's see, the third root and the reciprocal. Yeah, I could just do that. Negative 9 over 5x plus c x to the sixth and negative 1/3. I was thinking of taking the reciprocal, but I have to combine common denominators first if I do that. And we could do that. So the common denominators would be x to the sixth, 5x to the sixth. So then this would be 5x to the sixth in the numerator, x to the sixth, x to the fifth. I don't know.
Yeah, how do you deal with that? Drop the x and just keep the c. Maybe that's 3.5.
Yeah, you could combine this into one constant. But since this is an initial value problem, it would be good to talk about the difference between keeping this a c or keeping this into a 5. So, did I do this right? Did I combine the fraction right?
But you got to put the x with this down there with the c also, right?
Was there an x there? Yeah, I think it was just the 5. So if I find common denominators, I need to multiply this by x to the fifth. And then I need to multiply this by 5. So my common denominator is 5x to the sixth. The denominator becomes a numerator when I get rid of this negative power. And then the 1/3 is a cube root. I think that looks right. In any case, you could have just left it as this to help us solve for c. Since we have an initial condition, we can find a particular solution. So let me take our answer here and move on to a new page. So there's two views that we're looking at. And given your initial condition, let's find your initial condition again. Our initial condition is our initial condition says that when x is equal to 1, y is equal to 1/2. So instead of calling this 5c, we can call it a constant d. And then now you kind of have a choice whether to take your function, to take your explicit function that you solve for here, or you take your unsolved implicit answer here to solve for c, to solve for the unknown constant. But I just want to make a point that the c that you had here is different from the 5c that you have here. This is d. let's try this. Let's give the first 3 rows or columns, whatever. Well, the first 3 rows over there, you guys solve for c here on the first function. So when x is equal to 1, y is equal to 1/2, and see what you get. This half of the class, try to take this y equals the cube root of this thing and solve for d here. And then tell me what you get for your answers for your c and d, or for your unknown constant. If anybody has an answer, raise your hand, then we'll concur with another. You guys are doing this D, right? What did you get? 49?
Well, I got C. 49.
47, uh-oh. 49? $49. The other half of the room, was that easier? I mean, you guys didn't do the other side. What did you guys get? 49/5. Yeah. So in either case, you would get the same solution. They're off by this constant that we kind of merged together. So I don't know which was easier. Was this easy when you guys solved? The top one? Yeah, I think the top one, before you explicitly solve for y, I think that relationship here might be easier to solve for c in some cases. So I would have done this one, and then after I found out what c was equal to, then I would have tried to solve for y if I wanted an explicit answer. Versus doing the y equals to, and then trying to solve for the unknown constant after you've combined it with other terms. So this has a little bit more algebra, I think, that's involved. And we tend to like the algebra with numbers instead of with variables most of the time. So I guess what I'm saying is either case, you should, you can do either case, but for me, this probably would have been the easier move to solve for c here. So in any case, your final answer would end up being whatever this is. So y of x is equal to, if you've gone this far to solve for it, 5x to the 6th over 49 minus 9x to the 5th. Okay? But the key is, this is just the extra work to solve for the initial condition. The key to this particular technique is in the previous page. So let me go back there and I'll come back to this page. The key is to make the proper substitution. And remember that whenever you have to do a substitution, you have to take a differential. And in this case, the differential turned out to be du is something dy. And then we just, it's literally a replacement of du dx, dy dx. So you do your substitution. And if you can find a pattern here, you'll see that that substitution will yield to a linear equation, a first order linear equation. in the new variable that you found, which is u. After that, you do the integrating factor technique, and then you finish off solving for this. Okay? Any questions? Yeah. Not this. I mean, we just talked about it. So I was thinking we'll have a quiz next Tuesday, and the quiz will probably be on material that we talked about last week. So that would be integrating factor and exact equations. So I'll let this particular topic of substitution kind of simmer a little bit more in your heads before giving you a quiz on it. Okay. Any other questions? So this is the rest of our initial value problem to find a specific solution or particular solution. There's one more substitution that I think is kind of a weird substitution, but this one doesn't take in a special name like the homogeneous equations or homogeneous functions or the Bernoulli equation. Here, you just have to identify if your differential equation looks like it's really a function of ax plus by is equal to c. If you do a substitution where u is equal to whatever that term is, then you can use a separation of variables. So what types of differential equations would qualify under this special type of function? Oh, I don't think it has to be partial fractions. I think any of these would work. And we'll pick one. The first one looks clearly like of that form. The next one, number 24, doesn't quite look like that form, but you can argue that if you kind of massage it a little bit, then it might look like that. Yeah? So for the Bernoulli, Bernoulli equation is y to some power on the right-hand side. And so if you make the substitution, it should automatically turn into a first-order linear differential equation.
The one that you talked about.
Oh, the one that I'm introducing?
Yeah.
I don't...
I think we did separation of
some of them might turn out to be a Bernoulli equation, but some might not. So you have to be careful. I like this. If adding this extra one over here would make it not Bernoulli anymore. Or no, that's homogeneous. No, I'm not understanding. This is not Bernoulli, right? Okay. Well, in any case, if somehow you can make this look like a function that might look like it could be, like an ax plus by plus c business, then you can do the appropriate substitution. Like for this, for number 23, it's clear that ax plus by plus c could be x plus y plus 1, right? But for the second one, ax plus by plus c has to be x plus y plus 0. So we're not counting this 1 as part of the expression. So if somehow you can identify these things as a function that has this ax plus by plus c, you can do just a simple U-substitution. So let's do one of these problems. Which one should we do? We could do an initial value problem or just solve for the differential equation with 2 minutes left.
Yes.
Yes? Which one? Let's do number 30, for example.
Yes.
I don't think I'm going to get far with this. So number 30. So we're going to do a U-substitution here. We're going to let U equal to, and for this I probably want to just look at U equal to 3x plus 2y. And then I want to replace the dy dx with du dx, so I probably want to do a du dx business here. How's this going to go? No, that doesn't look right. Oh well. Does that look right? Yeah, it looks fine. All right, so make the substitution. Oh, I need to solve for this first. So this is going to be du dx minus 3 divided by 2. So that's what dy dx is going to be. So dy dx is going to be du dx minus 3 divided by 2, and that's equal to u over u plus 2. So this is supposed to be separable, and we just solve for du dx, bring the 2 over, and subtract the 3. So bring the 2 over and then subtract the 3. Well, let me do this in steps. So I need common denominators. This is u plus 2 plus 2u plus 3u, 5u plus 2 divided by 6, because that gets multiplied also. Thank you. And then it looks like I'm u plus 2 divided by 5u plus 6 du is equal to dx. So it looks like there's some way to solve for the left-hand side. I don't know if a U-substitution would work. I wouldn't use a U. So I'd probably split this up to 2 fractions, and then the first one you have to do some tricky substitution. The next one is just going to be some ln, and then solve for that. All right, so it looks like we're out of time, so you guys can try to finish this last type of substitution. So the quiz will be next Tuesday, and it'll be on integrating factors and exact equations.
Try to make general forms.